So this video is going to consist of two slides. One of them is just going to be a general description of the states of matter. And the second slide will describe what happens and how things go through changes in state. Now the states that I'm talking to are solid, liquid, and gas. And everything I write here is going to be stuff that you're going to need to know, and we will have sort of like a do now we get in based upon this so that we can build on it in class. So let's assume we're going to use as an example oxygen. And the reason why I'm doing that is to get away from the idea that the only substance that's solid, liquid, or gas is water, because it's not. There's many substances that you can put into all three of these phases. They don't happen at the same temperature or under the same conditions, but they can exist. So you have oxygen, or O2. I'm going to draw pictures of them, and they look like this. That's an O2 molecule, 2 atoms, it's a diatomic molecule. It could be chlorine or bromine or any of those Brinkelhoffs. Now, let's start with the solid description. Well, if I had a solid piece of oxygen, it would be like a solid piece of ice. It would have a shape, a definite shape. I might have a cube of ice, right? Sometimes I can get circular ice cubes, right? I can make a snowball that's round, okay? But it will definitely be in a definite shape. So solids have a definite shape. They don't just fit the shape of their container. You know, if you drop an ice cube into a round glass, it doesn't change its actual shape. It's got a definite shape, and it has a definite volume. Even if it's if it's a cube, you can measure its length and width and height just like we do in a density lab. If it's an irregularly shaped solid or something like that, you can just dunk it into a graduated cylinder and see how much it displaces the volume. So you'll have a definite volume that you can actually measure on any type of solid. For a liquid, let's say I'm sitting here with my bottle of water, right? So I've got a bottle of Poland Spring water sitting in front of me, and it's filled up to the tippy top. Now I'm going to show you a demonstration in class that will be interesting because, if it's a completely filled bottle of water, you can't squish it because it takes up a certain amount of space, and that's why you can buy liquids by volume. So if I buy a liter of a liquid, it's got a liter of liquid in there. I can't squish it and take up less space, and that means it has a definite volume, just like solids do. Right? But it doesn't have a definite shape, because if I take the cap off my liquid, well, I did a bad job of that. I can pour that liquid into I can pour that liquid into a cup, and it will take the shape of the cup I just put it in. I can pour it in any shape cup I want. And that means it has an indefinite shape. Another way of saying that is basically it takes the shape of the container you put it in. It takes shape of container. Okay, the other phase of matter is a gas. Now a gas, on the other hand, well, imagine you've got a basketball or a football, right? Like everybody heard about Deflategate, right? Now, if you watch, this is the worst football ever drawn here, okay, right? So there's my football. I think it's a football. Here, I'll make it look a little more like a football. Here, now it's a football. All right. So if you pump gas into a football, right, with a bicycle pump or something like that, and you fill it up with a little bit of gas, it takes on the shape of the football. But you can pump more gas or less and it still looks like a football. And what I'm trying to say is just by looking at the shape of the football, you really don't know how much gas is actually in there, right? You'd have to measure the pressure. That's what Deflategate was all about with the Patriots and the footballs. Well, just through the football, you can't look at that football and tell how much stuff is actually in there. And what that means is, for a gas, there's an indefinite volume. And an indefinite shape. I can take the air out of that football and put it into a basketball, or put it into a balloon that's shaped like a poodle. It will take on the shape of its container. It does not have a definite shape, just like the liquid. Depends on the container you put it in. And it has an indefinite volume, right? The same amount of gas in a thin-skinned balloon might spread out and take up more space, but because of the hard walls of the football, it's limited in how much volume it can actually have. Now, how do we view these at the submicroscopic level? Well, let's look at our solid. Our solid contains molecules that don't appear to be moving anywhere, and they don't fill up their container. So it's kind of like they're just stuck with each other like this. All right? So here they are. Here's our molecules of oxygen, and they don't even fill up the bottom of the container, do they? And they're the way I would think of this is really organized. And that's not like they're not moving, okay? The molecules are actually moving, but the only type of moving they have is the only type of movement that somebody standing still can. It's like that kid who's sitting there and he can't sit still, but he's not allowed to get out of a seat. He's kind of rocking back and forth and stuff, but not going anywhere. So we say the solid particles have what they call vibrational movement. So they can vibrate in place, but they're not actually going anywhere. Okay, so what happens when we turn into a liquid? Well, all of a sudden, okay, we can pour a liquid, can't we? Which means the particles aren't stuck to each other as much. Okay? And so when you get to the liquid, all of a sudden, not only can the particles vibrate, now here's the thing, they're still stuck to each other. But if you look at my drawing, what I want you to see is it's more chaotic and messy. I'm not going to change the number of molecules. I had 9 O2s in there, and I'm going to put 1, 2, 3, 4, 5, 6, 7, 8, 9 molecules in here. But what you're seeing now is they're still vibrating, but they're also able to sort of flow or rotate around each other. Like that. Okay? And so when you get to a liquid, you have what's called rotational movement as well. They're still stuck to each other. They're still very close to each other. Right? Now, you need to differentiate that from a gas. A gas, on the other hand, has a third degree of movement. And a gas is said to have, so this is solid, liquid, gas. A gas is said to have translational motion. And what that means is its molecules, I'm going to put 9 of them in there again, can go like this, bing, 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 and they can bang into each other, but they're not stuck to each other. And that's called translational motion. They're moving in these straight line paths, like bumper cars going in straight lines, banging into each other and banging against the walls. All right? And because there's so much huge amounts of space in between them, gases are compressible. And that means that explains why they don't have a definite volume. If I could put some more gas molecules in there because there's space for them, right? So there's 9 molecules in there fit into that space. Well, I could put a few more in there. Right? They bang into the walls more, they change the pressure, okay? But they can still take up the exact same amount of space. There's room for them, okay? So gases are compressible, whereas liquids and solids are not. You can't compress them. I can't squish a solid and take up less space, but I can definitely squish a balloon.